Hello everyone, welcome back. In this video, I'm going to finish the Challenger questions from Pathfinder in rotation chapter. Then I'll take up the next chapter. So this is the seventh question in that series there. So let me read the question. A uniform annular disk of outer radius capital R, so the outer one, annular disk, and inner radius small r is coaxially mounted on the fixed cylinder. So the middle one is the cylinder which is fixed, he said. Mind you, see there, it is directly attached, rigid to the ceiling. So the middle one is not rotatable, it is fixed. Cylinder, we call it as cylinder. And that has got inner radius slightly less than smaller. Okay. So that it can easily fit in and then smoothly it can rotate. The coefficient of friction between the disc and the cylinder is mu. So disc is the outer layer, cylinder is the inner layer. So between them he has given the friction coefficient mu. Light inextensible rope. So when it is light, whether it is rope or string doesn't matter, massless. We are going to neglect the mass of it anyway. Supporting two loads of mass M and capital M, which is greater than small m, passes along the upper half of the periphery of the disc there. This is upper half you have there. Fine. Now what is he asking? They are asking you to find acceleration of the load capital M. Yeah, capital M and small m will have the same numerical value of acceleration. If capital M goes down because it is heavier mass, the small m has to go up with the same magnitude of acceleration. Now he has given acceleration of free fall is g. Okay. Now in this question I have certain doubts there and certain things which are not specifically mentioned. Number one, what is the mass of the disc, that annular disc that they had mentioned, right? What is the mass of that annular disc? They didn't give that. So if they don't give it, we assume that it is negligible mass. So that is a safe assumption because they didn't give the mass of it. So that negligible mass will give a very useful result for us. Next they gave mu between annular disc and cylinder, all right. But they didn't give the friction coefficient between the rope and the annular disc. So probably it is not needed. Otherwise, maybe if it's needed, we'll try to assume it. But as of now, we know that it is not given. So that is the second part. And the third part is, now the disc, whether it is slipping on the cylinder or not, we don't know. So blocks will have to move. That means rope has to move. Now the question is, only the rope moves or even that annular disc also rotates? That is something that we don't know. So that is also not very clearly mentioned there. It is possible that annular disc is fixed, only the rope rotates, or otherwise annular disc and rope together can rotate with common angular velocity or different angular velocity also. So that point, whether annular disc rotates on the cylinder or not, that is also not mentioned there. Maybe required depending on the situation, we will take it. So this is basically a problem in the question. Question is simple only, just that the information is somewhat not very clear. You need to probably take some extra assumptions based on the requirement. Okay, let's go to the next slide here. So what is the strategy, what is the methodology that we are going to do here? They gave two masses and we need to find the acceleration. So simply we'll use Newton's law only, draw free body diagram and so on. There are two blocks, we'll draw FBD and try to apply Newton's law there. But one more interesting thing is that the annular disc that they had given is assumed to be massless because it was not given, mass was not given. But when it is massless, right, there are some interesting observations which you need to use here. Irrespective of acceleration of a massless body, irrespective of angular acceleration of massless body, net force has to be zero, otherwise it will have infinite acceleration, and also net torque has to be zero. So this is something that I am going to use here. Net force zero, net torque zero for the annular disc. Okay. So now let's look at this disc, only disc part. Annular disc is outer layer, the blue one is the cylinder part, forget about the cylinder. Now if you assume that there is a contact force between disc and the annular cylinder, annular disc and cylinder there, so there will be normal reaction and also there will be friction there. So if you assume that the contact is at the top, there is a gap, microscopic gap is there, the contact is at the top if you have there, then normal reaction will be pressing it up, and as it is rubbing on it, there will be friction also pulling it backward. So if you have that particular situation, because it is massless, net force has to be zero irrespective of the acceleration, angular or linear, Now you see vertical forces have to be balanced, meaning T1 and T2 together should balance normal reaction, okay. But the friction is not balanced here. So friction is not going to be balanced if you have this particular scenario. This particular scenario is not possible. If you have this kind of situation, the N and F resultant would be at some angle. That cannot be balanced by tensions which are vertically oriented there. So this orientation is not possible. It is not going to have a contact there. Probably it will have a contact somewhere else at some other position, not exactly at the topmost point. And that is what I am going to take in the next slide. So let's say this is a situation I have. Normal reaction will be tilted at certain angle, and friction is also perpendicular to N but tilted, so that the resultant of these two is vertically upward. Only then it can balance T1 and T2. The resultant of N and F, which is applied net contact force, let's call it as capital F bar, that should be vertically upwards. So the contact would not be right above the center, it will be a certain angle there, and N and F together has to balance the net contact. I mean, we will have to together give net contact force which is balancing T1 and T2 there. So that net contact force is root over N square plus F square, and that should balance T1 plus T2. That's what I had mentioned. See, T1 bar plus T2 bar plus F bar, which is the resultant of those two contact forces, must be 0, meaning F bar has to be vertically upwards, otherwise F is equal to T1 plus T2, which is root over N square plus F square. So that is one important equation from massless rod we have there. Okay, next we also have torque equation for it. Because it is a massless one, we can write torque, net torque 0. Torque about C, we are looking at center of the cylinder there. So due to T1, due to T2, due to normal reaction, due to friction, there are 4 forces acting. We will have to calculate due to each. Due to normal reaction will be 0 because N passes through center. If a force passes through a point, torque due to that force about that point has to be 0. That is understood. Now you see T2 and F are trying to rotate one way. T2 is trying to rotate this way, and F is also trying to rotate in anti-clockwise direction, whereas T1 is trying to rotate in clockwise direction. Because it is massless body, even though it may have angular acceleration, because it is a massless body, net torque about C has to be 0. From there I will get one more equation, T1 minus T2 equal to F into small r by capital R. F I didn't mention whether it is mu into N or not, because whether it is slipping or not I am not sure still. If I don't have to use that mu into N, I'll just take it like this. Depending on the situation, we'll see the assumptions there. So this is second equation we have here. First equation from translational equilibrium, not translational equilibrium, we should not say translational equilibrium. It is having acceleration, but net force is 0. And again net torque also 0. From there I got second equation there. Okay. Now we'll go for the blocks now. Let's look at the blocks. Each block will write the free body diagram. Capital Mg is going down against T1. So capital Mg minus T1 equal to capital M into A. Same way T2 is pulling it up against small mg, the smaller block. So T2 minus mg equal to small m into A. These are the two equations you will get from Newton's law applied for blocks there. So already we have these two equations 1 and 2. Now we got 3 and 4. Totally we have 4 equations now. But the number of unknowns, if you see, that are involved in these equations is T1, T2, N, F and A. 5 unknowns are there. 5 unknowns are there, but we have got only 4 equations. That's a challenge here. So with this as it is, we will not be able to solve now. We have to take extra assumption. That assumption is, let's say the cylinder or otherwise annular disk is sliding on the cylinder. If I take that assumption, then I will get one more equation, F equal to mu n. So I have to take this F equal to mu n, otherwise I will not be able to solve this question. So they would have mentioned that in the question there, that the cylinder is sliding. So that is not mentioned, that is why a little ambiguity. Let's say we have to assume it to be sliding, only then I will get the fifth equation. The moment I have fifth equation, then it is very simple. So you put F equal to mu n in the first equation, you will get this. If you put F equal to mu n in the second equation, you will get this. Solving these two, you will get T1 and T2 relation. I have just taken the ratio and applied component or dividend. So from there I will have one relation, T1 by T2. Now go for 3 and 4. You calculate acceleration from third equation and acceleration from fourth equation, equate them. Acceleration from third and fourth, equate it. You will get T2g equal to T1 by capital M plus T2 by small m. I have written everything in terms of T2 because this equation is there now, based on 1 and 2 together. I have taken this as gamma here. One big expression is coming. In the final answer they gave like this. That's why I have taken it. In the answer they gave that mu into small r by capital R into root over 1 plus mu square is taken to be gamma. So if I take that, I have T2 is this, right? By simply solving it, you do yourself, you will do it much better, but just that it is simply little lengthy manipulations there, solving of linear equations. Once I have T2, I can go back up to the second equation and substitute the fourth equation. I'll substitute there A equal to T2 by small m minus g, and then after that simple manipulation only. Don't worry about these equations, you can do it yourself, but final answer is this. So the final answer is matching with what they had given. That means the assumption that f equal to mu n, they have asked us to take it. There is no reason why it should be. It's possible that the annular disk will remain stationary and only the rope might slide. But the friction coefficient between rope and the annular disk, they didn't mention it. So the only way we can solve it by assuming the slipping between cylinder and annular disk. So with that I complete the solution there, and thank you very much for your time. Until next time, goodbye.